Let's get going. So good day, everyone. Good morning, good afternoon, good evening. So we are very happy to have Robert A. Wilson with us today to give today's OSMU lecture on Einstein's nightmare, is physics fundamentally discrete? Since 2004, Robert has been professor of mathematics at the School of Mathematical Sciences of Queen Mary University of London. In 2016, he took an early retirement from this position. However, he certainly, of course, continues to be very active in his research, as is evident, for instance, from his important recent findings. And in recent years, Robert's research has been mainly in applications of group theory and representation theory in fundamental physics. Robert obtained his BA, MA, and PhD from Trinity College, Cambridge during the years 1975 to 83. Subsequently, he was a research fellow at Jesus College and a lecturer at Girton College, Cambridge, before taking up a faculty position at the University of Birmingham, which he held until 2004 before moving to Queen Mary. His research in those years was mainly in finite group theory and related areas such as representation theory, some aspects of combinatorics and computational techniques and algorithms applicable to finite groups. I would in fact invite you to visit Robert's homepage at Queen Mary to get a feel for the extraordinary breadth of his research, which spans both mathematics as well as fundamental physics. Particularly noteworthy is his recent research on Clifford algebras and on the groups E8 and E6 in relation to the standard model, something we have already heard quite a bit about. Robert has also authored and co-authored several books, including the very well-received Atlas of Finite Groups, as well as the Finite Simple Groups, Graphs, Colorings, and the Four Coloring Theorem, Atlas of Brouwer Characters, as well as a book on linear algebra. It's really a lot of work, I must say. I should mention Robert is also an accomplished musician and plays the viola. He was principal viola in the Sinfonia of Birmingham for several years and also plays the violin and piano. It's a pleasure to have you with us today, Robert. Kindly go ahead.
Thank you. Thank you for that introduction. So I'm going to present today what is perhaps a rather controversial picture of fundamental physics, where most people's view of the theory is that it should be based on continuous variables and differential equations and so on. And my view is that actually it can be simplified, and that what's actually fundamental is discrete symmetry. So let's get going. And this is roughly the contents of what I'm going to say. I'm going to try and analyze the problem of unification and so on, and present a roadmap for what I think is a solution. And then I'm going to try and explain not the full model, but a toy model to get going, to see how the methods work. So it's a toy model of colors and generations, really. And before moving on to development of the rest of the model, and finally to synthesize it into what I shouldn't call it a theory of everything, but I am calling it a theory of everything. And then if we have time, we'll have a look at some predictions and speculations based on the model. So that's the plan of campaign. So let's look first at what the problem is, or what I think the problem is. And let's start with Einstein's words from 1954. I consider it quite possible that physics cannot be based on the field concept, i.e. continuous structure. In that case, nothing remains of my entire castle in the air, gravitation theory included. Well, I don't think it's quite as bad as that, because for a start, Einstein isn't denying that the field concept is extremely useful. All he's denying or questioning is whether it's really fundamental. And that's where I kind of agree with him. What we want to try and do is get the continuous fields out of something more fundamental. Where are we? Next one. And if we can do that, then it turns from a nightmare into a dream. So let's see where we go. Let's start. The most basic things we need in the standard model are the Dirac gamma matrices. Basically, if we haven't got the gamma matrices, then we can't do anything. And I wanted to make the Dirac matrices into a finite group. So I've got to just multiply them together. Okay, and we've got scalars of order 4, plus or minus 1, plus or minus I, and then we've got 4 matrices, independent matrices, gamma naught, 1, 2, and 3. So there are 2 to the 6 elements altogether. That gives us a group of order 64. And it can be written, and usually is written, as a Kronecker product of 2 copies of the Pauli matrices. So we've got, in this picture here, we've got Z4, the scalars of order 4, and then we've got 2 copies of the quaternion group. That's the basic structure that we've got, but we also need 3 generations and 3 colors. So we need to multiply by 9 and get a group of order 576, which happens to be 24 times 24. So what I want to do is replace the Pauli matrices, which is a group of order 16, by a group of order 24, and have 2 copies of it, Kronecker product or direct product, really, of 2 groups, of 2 copies of the same group of order 24. And that should give me all the Dirac algebra and the 3 generations and the 3 colors all in a single algebraic object. So that's the idea. That's what we're going to try and do. And the type of object we're going to use, the algebra we're going to use, is a group algebra, which is actually a very easy generalization of Clifford algebras. So Dirac algebra is a type of Clifford algebra, and so we just want to generalize it so we can use elements of order 3 as well as elements of order 2. That's all we want to do, really. So if we take the Pauli matrices, let's call them X, Y, and Z, they generate Clifford algebra CL3 naught, which is 2 by 2 complex matrices. And if we do the group algebra, so the Pauli matrices generate a group of order 16, as I've already said, and the group algebra of this group of order 16 is a 16-dimensional real algebra, which has got 2 by 2 complex matrices and 8 copies of the real numbers. And these real numbers are really representations of groups of order 2. So X, Y, and Z can act as +1 or -1. That's all. So we've got 3 quantum numbers, 3 independent quantum numbers in there. So it extends the Clifford algebra by some quantum numbers. And here I've just restricted down to the quaternion group without the complex scalars, and taking J and K as generators. So here are the relations that define the quaternion group. And all I'm going to do is change that. So I'm going to change a couple of 2s into 3s, and that is all. Okay, and that generalizes the standard model, or it generalizes the Dirac algebra to include the 3 generations and 3 colors. So so that's what I'm going to do. So this group is 24, this group of order 24, this group algebra is a 24-dimensional algebra. And it turns out that the structure of this algebra is like this: real numbers plus complex numbers plus quaternions plus 2 by 2 complex matrices plus 3 by 3 real matrices. Which means that it looks very much like the standard model, but not quite. So if we take the elements with real determinant 1 in each factor of this, well, we've got nothing left in the real numbers. We've got U1 in the complex numbers. We've got SU2 in the quaternions. We've got SL2C and the scalars U1 in the complex matrices here. And then we've got SL3R in the 3 by 3 matrices. And that looks very much like what we get in the standard model, with the gauge group U1 cross SU2 cross SU3 cross the Lorentz group SL2C. So we've just got U1 cross SL3R in place of SU3. And the question is it good enough? Well, we've seen this problem before. We've seen U1 cross SL3R in Corinne and Tevian's talks, and they believe that that's good enough for the standard model, and so do I. So one of the things I'm going to try and persuade you of is that it actually is close enough. So we've got the finite group and we've got the gauge groups, these Lie groups. And we can multiply them together in any order. We can have the finite group acting on one side of the gauge group on the other side, or any combination we like. And what happens? If the finite group acts on both sides, we've got no continuous variables at all. We've got no differential equations, nothing we can measure. All we see is internal symmetries. Okay, fine. If we take the finite group on one side and the continuous groups on the other, then we've got some operators, maybe in the finite group. We've got some eigenvalues in the continuous. We've got some continuous variables. We've got things we can measure. And so this is where we should see quantum mechanics in the standard model. And if you take the continuous groups on both sides, then there's no quantization. There's no elementary particles. There's no quantization of charge or anything like that. And we should recover classical physics. So the beauty of this picture is we can get classical physics, we can get quantum physics, and we can get internal symmetries all in the same model, all at the same time. So that emergence of classical physics isn't a problem. Well, you may not believe that, but let's see. I'll look at a very small example first to see if I can persuade you that this works in a toy case. So let's explore a toy model. The smallest possible example we could have is a cyclic group of order 3 inside U1. So it's a rotation group of an equilateral triangle inside the rotation group of a circle. So for let's look at this group Z3. Here's the multiplication table of the group. E is the identity element, F and G are the rotations of order 3. What do we know? F times F is equal to G. That's basically all that happens. It's a very simple multiplication table. And now I want to explain what the group algebra looks like, because this is a thing that may not be familiar to many people in this audience. So the basic idea is you can add together E's, F's, and G's, and with any coefficients you like. And I've taken E plus F plus G, just add together all the elements of the group. And if you square that, you find you get 3 times E plus F plus G. Well, if they're real numbers, you find E plus F plus G is equal to 3. Okay, so you've got the 1 in this copy of the real numbers is just E plus F plus G over 3. And perpendicular to that, you've got a complex number. So 2E minus F minus G, if you work that out, also comes to 3 times itself. So that's another copy of 3. That's a copy of 3 inside the complex numbers. And then F minus G is also orthogonal to both of those. And if you square it, you get minus 3, and therefore you get the complex numbers. Okay, so this is how group algebras work in general. You take all linear combinations and you do a bit of mathematics to break it up into these matrix algebras. And here we get reals plus complexes. And what does that tell us about physics? Well, let's look at internal symmetries first. Internal triplet symmetries means colors. That's what the internal triplet symmetries are. I'm basically going to think of E, F, and G as the 3 colors. In which case, E plus F plus G has no color, and it's actually going to denote electric charge. And if you look at the complex number part, you get the 3 colors adding up to 0. So you get color confinement. So it's looking good so far. And this is my analysis of what a neutron looks like. You take the 3 cube roots of 1 in the complex numbers. Here they are. 2e minus f minus g over 3 is the 1. And these other ones multiplied by f and multiplied by g give you the cube roots of 1. And if you think of this as being a neutral particle, because we've taken the charge away, it consists of 3 quarks with colors E, F, and G. And now I can work out what the charges on the quarks actually are. Because I take a particular color, let's take the color E, I multiply by the charge, and I get 2/3 of the unit of charge. Okay, so I get 1 quark in a neutron with charge 2/3. And I take F or G, I do the same calculation, I get 2 down quarks. Okay, so I get the quark structure of a neutron from the internal symmetries there. Now, if I go up to the next level of interpretation, I'm going to the quantum mechanics level, the measurement level. There I can actually measure things. I can measure masses, and therefore I get generation triplets. So let's just consider that we take a triplet of electrons, electron, muon, and the tau particle, 3 generations of electron. It still splits as reals plus complexes. The reals still contain the electric charge. The complex number now contains the differences. It contains the mass that we can actually measure. And this is where things get quite interesting. I think I prefer to, before we do the calculation, I'd like to show you the picture. Okay, so here's the electron, the muon, and the tau particle on the vertices of an equilateral triangle. Well, it's almost equilateral. It's about 59 degrees. And there's a mass axis here. I've drawn it through the tau particle for convenience. And on this scale, you can see the electron mass is almost 0. The muon mass is about 1/17 of the tau mass. And so you can see from the picture that that angle is a little bit more than 30 degrees. And it turns out to be 33.024 degrees. Now, do you want to see the calculation? I don't think you do you? There is a calculation anyway. It's quite straightforward. So the question I'd like to ask you is, do you recognize this angle? Is it an angle that you know in the standard model of particle physics? No, you don't know?
Not too close to the weak mixing angle, little off, no?
I'm sorry?
It's not close to the Weinberg angle, it's a little off.
It's not the Weinberg angle. Let's look at the picture again. It's an angle that tells you about a difference between an electron and a muon. It's an electron-muon mixing angle. So a lepton mixing angle. So it's in the PMNS matrix, and it's theta 1, 2 of the PMNS matrix, which is actually experimentally measured at about 33.5 degrees plus or minus 3/4 of a degree. So it agrees with the experiment. Well, you might not think that's very convincing, but let's carry on and see if you believe it when I show you some more angles.
Could we see the calculation a little more? Yeah.
The calculation.
Yeah,
Okay.
I wanted to say, if you could please explain what's going on here.
So the mass of the torr minus the mass of the electron, mass of torr minus mass of mu, in the picture here, they are, so mass of torr minus mass of mu is this length here along the mass axis. And that divided by the side of the equilateral triangle is the cosine of theta. Okay, you do the same thing on the other side, you get 60 minus theta, and you get the tau minus the electron. Okay, so let's go back here. Cos of 60 minus theta is the tau minus the electron. Cos of theta is the tau minus the muon. Now you just do the calculation. Trigonometric identities reduces this left-hand side to what have you got? Cos plus sine. The cos bit gives you a half for cos 60. The sine gives you √3/2 tan theta. And this putting in experimental values here is a little bit more than 1. And just calculate it. And it comes out like that. Okay?
Yeah. Thank you.
Well, that was the middle level of interpretation. What about the classical level of interpretation? Now we haven't got a quantization. We haven't got 3 generations of electron. All we've got is mass. But we've got a mass plane. It's not a scalar, it's a plane. What's going on? Well, I think it's a failure of the weak equivalence principle. Mass isn't a scalar, so inertial mass and active gravitational mass are actually pointing in different directions in this mass plane. Almost exactly the same, but not quite. So that's the first prediction of this toy model. The weak equivalence principle is false. Now, this is probably a bit premature to say that it splits the gravitational field from the electromagnetic field, because this only really happens when we move up into the full model. But just as it's dual to this, because we've got a real charge and a complex mass, but dually we have a real gravity and a complex electromagnetism. Maybe I can explain that later when we get there. But if we now think back to the other two interpretations, if we go back to the internal version where we were talking about neutrons, we can think about quantum gravity by quantizing the mass plane with neutrons. And astronomers normally only think of neutrons. They don't think that it makes any difference whether you have protons or neutrons, and electrons are too small to bother with. But if you do this now at the middle level, the quantum field theory level, you quantize with 3 generations of electrons. And it matters which generation your electrons are in. And you might think all electrons are electrons in practice, but do we really know that? Because neutrino oscillation, if we talk about the neutrinos instead of the charged leptons, then we've got neutrino oscillations. And we really don't know what happens there. So there's some questions that might be very interesting for quantum gravity. Okay, so this is my summary of what we've done so far in this toy model. Let's just have the whole lot at once. So just from Z3, we get the quark charges, we get color confinement, we get the electron-muon neutrino mixing angle from the PMNS matrix, we get a canonical splitting of mass from charge. And if you believe what is a bit premature here, we also split gravity from electromagnetism, and we get a clear indication that neutrinos are required for quantum gravity and must be responsible for failure of the weak equivalence principle, because it's the oscillations between electron neutrinos and muon neutrinos that are causing the weak equivalence principle to fail. Okay, that was just a group of order 3. I basically say, assume there are 3 generations of electron. Then all this follows. So let's try and develop a full model. So what we've done so far is just talking about the group U1. So let's now look at SU2, where the finite group, the obvious finite group, is a quaternion group. Yeah, well, you know what the quaternion group is, and its representation theory, it has 1 representation in quaternions, and it has 4 real representations, the trivial representation, and 3 doublet representations. So that's what the group algebra looks like. And we can try and analyze this and see what happens. So first of all, we extract the gauge group as the norm 1 elements of the quaternions. So from the finite group, we get the gauge group, plus 5 real scalars. What are these 5 real scalars? Well, I'll come back to that. First of all, I want to just make this remark that in order to get the real representations, what you really do is take a quaternionic tensor product of the quaternions with themselves. Now, the definition of a quaternionic tensor product is that it's gauge invariant, which is this equation here. Tensor product of 2 quaternions, Q1 and Q2, is the same as if you multiply Q1 on the right by any unit quaternion and Q2 on the left by the quaternion conjugate. So you can swap them from one side of the tensor product to the other and they all cancel out. So quaternion tensor product is very important for the entire model, in fact. But I want to look at the quantum numbers. These four copies of the real numbers, they contain quantum numbers. What are they? Well, what I think they are is some kind of neutral charges. So this is an important table, so let's spend some time looking at this. The real part here is the trivial representation. It's the same as it was before. It is the electric charge, okay? So I've got electron, muon, and tau all with charge -1. I've got a proton with charge +1. I've got a neutron with charge 0. I've got the proton and the neutron having all three colors, I, J, and K. I've got the electron, muon, and tau differing in the generations. So here, I, J, and K are representing generations rather than colors. And I've got a generation symmetry that acts on the leptons by cycling I, J, and K, but that acts as color symmetries on the baryons here. Okay, so there's a few slightly speculative things here, but I hope you'll see that it works. Now, here's the real reason why it works. If you add up the quantum numbers as quaternions, you take the E, mu, and tau here, you get -3 charge, and you get 2 I plus J plus K for the rest of it. So if you now add 3 protons to get rid of the charge, then you get an extra 3 copies of I, J, and K, and so you get 5 copies of I plus J plus K altogether. Now,
can I ask a question, please?
Yes.
Yeah, so I'm confused why you consider proton and neutron at par with the fundamental leptons, because we know that much of the proton mass, for instance, comes from QCD self-interactions and not from the quark masses themselves. So how do I get, I mean, you already got QCD interactions into the picture here?
No, I haven't. That's why I'm not talking about quarks and I'm only talking about the baryons.
Mm-hmm.
Because this is only talking about weak force. So I can talk about a neutron decaying into an electron and a proton and an antineutrino, but I cannot talk about the quarks inside the proton and the neutron.
Okay, thank you. Mm-hmm.
And this equation 13 here, I've really presented it backwards, because the equation 13 I discovered in 2015, and this stuff I only discovered this year. And the point is that equation 13 is an equation that balances not only the charge, which is obvious, but it balances the mass, which is not at all obvious, but it's true. And I've actually managed to publish that, so you can look it up and see that it actually is true to within about 1/10 of a standard deviation. So it's within experimental accuracy, that is what it is. Which means that these I, J, and K, or this quaternion now, can be used to quantize mass. Not for the quarks, but only for these 5 particles here. So we're in a 4-dimensional space, and we've got a mass direction. We can work it out. And this is what it comes to. I've written this in units of EV over c squared, but you can write it in any units you like, because all that matters is the ratios of these coefficients. So there are three parameters here, which you can express as mass ratios, but you can also express them as mixing angles. So here they are. The first one I took, so minus m naught plus m1 plus m2. So that's minus 1 plus I plus j. That's the electron. And m naught here, this value is the difference between the neutron and the proton. And so you've got the ratio of the electron mass to the difference between the neutron and the proton. And it's an angle between two lines in this four-dimensional space, or between a line and a plane, or something like that. And this is what the angle comes out to be. Do you recognize that angle? Is it an angle in the standard model of particle physics? I believe it is. I believe it is the CP violating phase in the CKM matrix.
Mm-hmm.
That's what I think it is. Don't ask me why, but that's what it is. The next one here is a neutron property, okay? M1 plus M2 plus M3, that's I plus J plus K, that's a neutron property. And we've got this angle of 2.3 degrees related to the neutron. What is it? Is it an angle in the standard model of particle physics? Well, it's to do with neutrons. I think it's a quark mixing angle. But it fixes the first generation, because it's a property of the neutron, which has only first generation quarks in it. So all it can be is the mixing angle between the second and third generation of quarks. And it is, to within experimental error, it is. And this third one here is a bit more mysterious, but it's cos squared of an angle that you will recognize as the Weinberg angle, the weak mixing angle.
Mm-hmm.
Cos squared is there for complicated reasons that I can explain, but probably won't. So what have we got now? We've got four mixing angles from the standard model of particle physics, and all we've done is we've taken the cyclic group of order 3 and the quaternion group and looked into their group algebras. Okay, it's not a full unified model yet, but we're getting there. Let's look at the strong force. This is where we actually do see some differences with the standard model. And I claim that the group we need is the alternating group A4, which is a group of order 12, which is the rotation group of the regular tetrahedron. And the reason I think it's that is because the group algebra is real numbers plus complex numbers plus 3 by 3 matrices. So it has the U1 cross SL3R that we want for the strong force in place of SU3. And this is the best we can do with the finite group algebra. So this is the best group that we can hope for. So the question is it good enough or is it not good enough? Well, I think it's good enough because we've got a representation, we've got a real three-dimensional representation of SL3R. And we've got a complex one-dimensional representation of U1. So we can tensor those together and get a three-dimensional complex representation of something. We can make SU3 act on that if we want. And if we then tensor this complex three-dimensional representation with its complex conjugate, then we tensor R3 with R3, and we tensor C with its complex conjugate. We tensor a complex representation with its if we tensor a scalar, what do I say, a one-dimensional complex representation with its complex conjugate, you get the trivial representation. So that's not giving us any information. All we've got is R3 tensor R3, and that's what we have as a representation of the finite group. We get two copies of a three-dimensional representation in there. So this means that we can take out the scalars, this diagonal matrix here, and we're left with a copy of the complex numbers, which is the trace zero diagonal matrices, and two copies of R3 for the off-diagonal matrices. So we can get the Gell-Mann matrices out of this and use them in the standard way. So I think that's close enough to the standard model. Now, if we go up to the second level, the measurement level, we've already looked at the R plus C part of this in the toy model RZ3, and we can do exactly the same here to lift now from the color level to the generation level. And so what does it tell us? Well, I've already told you actually what the four rotations are here, because those happened already in the earlier models, the earlier toy models. And I've got four rotations which are identified as mixing angles, and there are 8 boosts, which, well, the boosts are basically masses that we measure, and I've already given you 4 of them, the 3 generations of electron and the proton. But now we're wanting to talk about the strong force instead of the weak force. So we probably want to throw out the proton and put in some quarks instead, which means we've got room for 5 quarks. Or if we're only talking about mass ratios, we've actually got room for all 6. So this is just a sketch. I haven't done the details here, so I don't know what really happens, but at least there's enough in the model to contain all the parameters that we need. And now what about the classical level? We've already seen that R is the charge, C represents the mass plane, and the 3x3 matrices, well, at the classical level, you'd normally think of these as vector fields. You'd have 3 vector fields. And what are they at the classical level? Well, we only have 3 vector fields at the classical level. We have the electric field, the magnetic field, and the gravitational field. So that's what they have to be. There's no choice. That's the Newtonian gravitational field. But we haven't got general covariance. We haven't got general relativity. We've only got spatial covariance. We can only mix space dimensions together. We cannot mix space with time. So it's a theory of gravity that's somewhere in between Newtonian gravity and general relativity. It's neither one nor the other. It's somewhere in between. So I'm calling it spatial relativity, just so that we can get completely confused between spatial relativity and special relativity. Mm-hmm. Okay, so in spatial relativity, you have only 6 dimensions of the symmetric rank 2 tensors instead of 10. I think since I'm getting, well, I think we'll just go through this fairly quickly. In the classical level, SL3R actionis, these are irreducible tensors. If you just take spatial rotation and you don't stretch space at all, then it splits as 1 plus 5. That is a spin 0 representation and a spin 2 representation, which you might want to call a Higgs field and a spin 2 graviton, or you might not want to do that. But if you go to the finite group, then R5, the spin 2 representation, splits as C plus R cubed. So it splits as a Newtonian gravitational field plus a correction. And they're separate. They don't mix together. There's no spin 2 graviton. So by looking at the classical gravity that comes out of this finite model, we can go back and look at how to quantize it. We can go back to the previous level, the quantum level, and quantize gravity. Okay. So now we've basically done all the work. We just need to stick everything together into a unified model. And since I haven't got very much time left, I'll maybe skip over some of the unimportant things. The binary tetrahedral group, well, you know what a tetrahedron looks like and how it's got 4 vertices, and so you've got 8 rotations of order 3 corresponding to those. And you've got 3 rotations of order 2 corresponding to an axis between midpoints of opposite edges. Now, if you go to the binary tetrahedral group, you lift from SO3 to SU2, and you get quaternions. And here are the quaternions. And my generators are going to be, I'm going to take Z to be the quaternion K and W to be 1 minus I minus J minus K over 2, so that I satisfy the relations that I told you about earlier. And there is a remarkable fact that so W here is giving you a complex structure. I'll show you the complex structure in a minute, but you would think that if you invert W, you take the complex conjugate, you get the same thing, but you don't. Because ZW cubed is -1, but ZW inverse cubed is +1. So complex conjugation in the standard model is not a symmetry. That's where chirality comes from. Mm-hmm. So to really see that, we need the representations. So here's a summary of what the representations look like. We've got the trivial representation R. We've got a one-dimensional complex representation, which is two-dimensional real, which has these values. So the trace of the element of order 3 is -1. There. We have a three-dimensional real representation. Then we have a one-dimensional quaternionic representation, which is four-dimensional real, and a two-dimensional complex representation, which is again four-dimensional real, and that looks like a Majorana-Weil spinor or something like that. But what is important to notice is the W column here. The quaternion spinor here is completely different from the complex spinor. because the W symmetry, the generation symmetry, the color symmetry acts differently on those two spinors. That is the crucial thing that enables us to go way beyond the standard model. So I've already explained what the group algebra is, and we've already seen most of it. We've seen R plus C using Z3. We've seen R plus C plus M3R using A4, the strong force. We've seen R plus H using the quaternion group. The only bit we haven't seen is the 2x2 matrices, where we see the Lorentz group. And another U1 of complex scalars, if we like. What does this tell us? This tells us that the Lorentz group, you don't have to put the Lorentz group in there. It is already there. As soon as you have electromagnetism and the weak force, you have the Lorentz group for free. So space-time emerges from quantum electrodynamics and the weak force. It's not a background that's independent of particle physics. Again, I should probably just skip over this. The basic principle is that all the representations contain infinitesimals, because you can project from the finite group onto any representation, and the elements of the finite group give you these infinitesimals or quantum variables of some kind. And to get differential equations, basically what you have to do is multiply some infinitesimals together. You multiply an infinitesimal distance by a charge density or something like that, and you add them all up, and you get integral equations, and you get differential equations. So I'm not going to explain the technicalities of that, but I'm just going to show you how tensor products of representations in principle give you all the differential equations you need. And we get 12, so the bosonic part, that's the reals plus complexes plus the 3x3 real matrices. As a representation, the matrices split up into 3 rows. And that factorizes as a tensor product like this. Trivial representation plus R3 tensored with R3 comes out and gives you all of the fields. But here's a remarkable coincidence. You can get it also by tensoring with R plus C instead of by tensoring with R cubed. Now, what does this mean? R cubed, tensoring with R cubed is differentiating with respect to space. Tensoring with R is differentiating with respect to time. And C here is the curvature. This is the extra bit of spatial relativity that comes into the Einstein field equations. Well, if you were doing this in general relativity, you'd put time on the right-hand side as well. So you get R plus R cubed, tensor R plus R cubed. You split it up into a symmetric part for gravity and the anti-symmetric parts for electromagnetism. And you get this lot here. You get 2 copies of R, and you get 4 copies of R cubed when there are only 3 in the group algebra. So you've got some redundancy here. You've got some things that have no physical meaning. Or at least in this model, they have no physical meaning. So you just throw them away. Well, what does that mean? Well, what you've got to do is subtract off a copy of R and a copy of R cubed. So you've got to subtract off a scalar and a vector. So from the tensor, which means that you've got a tensor vector scalar theory of gravity. The Einstein tensor stuff with an extra vector and a scalar added on, but actually they should really be subtracted off. So that's the relation to Mond and theories of gravity. The other thing we need to look at is the Dirac equation, which is the fermionic part, where we take a spinor, H, tensor with R cubed, that gives me all of the fermionic part, all of the spinor part of the group algebra, 12 dimensions of stuff. But it can also be written as H tensor with R plus C in the same way. What's going on here? Tensor with R cubed, those are the spatial derivatives. Tensor with R, that's the time derivative. Tensor with a complex number, what's that? That's the mass term in the Dirac equation, the complex mass term. Well, of course, if you're doing it in the standard way, you take the time derivative across the other side, and so on. But you lose some information by doing that. You lose the three generations by making it into a complex tensor product instead of a real tensor product. But it is basically the Dirac equation. And again, you lose the distinction between the quaternions H and the complex spinor C squared. You lose a very important part of the model that is essential for describing three generations. That's why the Dirac equation doesn't have the three generations in it. And here's just a remark that if you want to get from quantum physics to classical physics, you can tensor H with itself, this quaternion tensor product that I mentioned before. And I think I'm running out of time, so let me just mention two features of this model. One is parity violation. Well, I've already said it's a chiral theory, but let me say it again. The parity symmetry negates the spatial part. This negates R3. And if we look at this H tensor H thing here, if we negate R3 while fixing the charge, then we have to take the quaternion conjugate on H. And that swaps left multiplication with right multiplication. I can't do that because in particle physics, left multiplication is a gauge group and right multiplication is a finite group, or the other way around. I can't swap the finite group with the gauge group. So this model violates parity, as it should. It also violates CP. The reason here, I mean, CP you would think would be okay because it negates both R and R cubed, so it should be all right here. But it now splits the R plus R cubed, which is negated, from the complex mass term, which is fixed. So CP violation is a consequence of non-uniformity of the gravitational field. And here is the experimental proof. I can tell you what the CP violation of neutral kaon decay is exactly by looking at how the gravitational field changes over the size of the experiment. The experiment was 57 feet long. the angle between the gravitational field at one end of the experiment and the angle at the other end of the experiment is 0.55 of a second of arc, which means that the proportion of short eigenstate kaons that you get is the sine of this angle, which is 2 parts per million, which is exactly what was observed in the experiment.
Okay.
And since I've run out of time, I will stop there. Thank you very much.
Okay, great. Thanks so much, Robert, for a very interesting and fascinating talk. It's quite amazing how much you get out of putting seemingly very little in. So we can open the talk for questions, please. There were some remarks in the chat. Start with Hillary and then Daniel and then Bernd and then go on to other members. Hillary, please go ahead with your comments.
It was just when he was talking about quark mixing. And I was wondering if that might have consequences for the lifetime of the neutron. Because there is this thing called the neutron lifetime anomaly, which is depending on how you measure the lifetime of the neutron, you get 2 different answers.
Well, I'm not a physicist. I can't really make predictions like that, but I would expect it could. It could have something to say about the neutron lifetime anomaly.
Okay, if this just first question is over, then we go to Danielle.
Yes, I would like to know if, well, you have done everything with the binary tetrahedral group. Have you tried other like binary cosahedral group? And if so, why it was ruled out?
Yes, I did try the binary octahedral group, the binary tetrahedral group, and various other similar groups. And for about a year, I was convinced that the binary icosahedral group was the correct group to use.
Mm-hmm.
But the group algebra is much too big. It has general relativity in it, but it also has 5-dimensional space times and all sorts of things that I didn't want and didn't think I needed.
Okay, it was too big at the end of the day, but so there was not a specific reason to rule it out, apart from the fact that it was not conservative. I mean,
yes, it's Occam's razor. That's really all
okay.
it is.
Okay.
Okay, Bernd, please go ahead.
Just a brief question. Is the graviton mixed with the Higgs field in your model?
No, absolutely not.
Okay. This was one slide where you said you have the Higgs and the graviton in some representation. So, or basically, do you have then an additional scalar field for the tensor vector scalar field theory, which then incorporates Mond?
Well, the basic idea is that instead of adding a vector and a scalar field to the tensor field that you've got in general relativity, I subtract them off because I think the tensors in general relativity are too big.
Okay.
They involve messing around with time, mixing time and space, and my model doesn't allow you to mix time with space.
I see. That's important. Thank you.
Yeah.
And there's a new message in the chat, so go ahead, Mr.
Great. Go ahead, Bernd. Anything more?
No, I'm done with my question, so
Okay.
Anthony can continue.
Yeah, go ahead, Anthony, and then David after that. Go ahead, please, Anthony.
Okay, thanks very much for the talk. Just a question on, in fact, the slide that is up at the moment. So this seems to suggest you need a different analysis for each experiment. I mean, it hasn't just, CP violation isn't just in one experiment. how does this compare between experiments?
I don't know. I haven't looked at any of the other experiments. I looked at the first one and found that it worked. And
but I mean, the effect is meant to be, a fundamental thing that isn't just going with the particular length in an experiment. Or you've worked it out here in the context of, you believe it's a non-uniformity of the gravitational field, but you could test that by looking at the different experiments and seeing if the different setup in each experiment actually led to the right results given your explanation.
That is true. I could, if I knew where to find the experiments and stuff. Yes, that is something I should probably do, but I haven't done it.
Okay, can I just ask one more question at this point?
Please, of course.
Which is, in relation to the Dirac equation, it looked as though you were going to violate covariance, space-time covariance, and the way you were asking for that to be set up, and the time derivative essentially split from the spatial derivative. Am I misunderstanding that?
Well, the Dirac equation that I wrote down is quite a bit more complicated than the standard version. How do I get rid of that from there? Basically, because the standard Dirac equation confuses the quaternions with a pair of complex numbers. Or the Dirac equation has two spinors. I have three, because I've got H, the quaternionic spinor, and I've got two complex spinors.
Okay, but you seem to have a rigid split between space and time. I mean, not just here, but elsewhere. I can't see even special relativity in that.
Indeed. Yes. Yes.
Well, you seem to say earlier that, okay, we're not getting general relativity, we're only getting special relativity. And now you seem to be saying we're not even getting special relativity.
Well, it depends what you mean by special relativity. You see, we have got SL2C, so we have got a copy of the Lorentz group.
And can't that come in here then to mix up the space and time? Surely that must be what
yes, but that's it can do that, but that is incompatible with the internal symmetries of the elementary particles.
Ah, right.
So
the Dirac equation, you explicitly said the R cubed here is space, and the R was time, and they're not internal, that is space and time.
Well, I also said that everything in the model has an interpretation at three levels.
Uh-huh.
So these representations can be thought of as representations of the finite group, and they can be thought of as representations of the gauge group. Here, as a tensor product, here everything is a representation of the finite group. So there is no Lorentz group acting on this equation here as a tensor product of representations of the finite group. You have to switch to the next level to get R cubed as a space representation and R as a time representation. and then you can get the Lorentz group, but then you've got the Lorentz group acting on one side only. The Lorentz group is a classical symmetry or relativistic symmetry. It acts on both sides. So it's all in the difference between the different interpretations of the Lorentz group.
Okay.
The Lorentz group at the relativistic level or classical relativistic level, you've got the continuous group acting on both sides. The Dirac equation, you've got a continuous group acting on one side and a finite group acting on the other. Now, you can make the the Lorentz group here is acting on the spinors, not on the r plus r cubed. Because if it's acting on r plus r cubed, it has to act on both sides. It's acting here only on one side, so it's acting on the quaternions, acting on the spinors. Yeah, it's difficult to explain this without looking at all the details. So hopefully, I forgot to put down the references here. There's a new version of my paper on this on the archive yesterday, in which I try to explain these things in much more detail.
Okay, well, thanks. I'll take a look at that.
Thank you. Thank you. David, please go ahead.
Thanks for the talk. Yeah, there were some interesting ideas there. Finite groups in these ways. That's new to me. So,
Sorry, line is not clear, David. Line is not clear.
yeah, my microphone isn't very good. Sorry. I'll have to get a better microphone. I'll have to find it.
Now it's better. It's better now.
I'll just try to talk into it. I would just maybe consider looking into the ADM formalism. I don't know, just because there's kind of a precedence there for people picking out the spatial part of the metric general relativity. So I don't know if that would maybe help the story or not. But I just figured it's something to mention because that's just an example of where people part of the metric.
Yeah, maybe what I could do, David, I'll also read out your comment so that more clarity is added because of the voice problem. David says, I suppose GL3R over SO3 would give the 3x3 metric in the ADM formalism, or in linearized gravity, one can take the de Donder gauge to isolate 6 degrees of freedom instead of 10, with 4 redundant degrees of freedom, similar to how the photon has 1 redundant degree of freedom. So I think, Robert, the question is, can you work with the ADM formalism in a specific foliation where the dynamical variable is the 3x3 metric? Is that what you're saying, David?
Yeah.
Robert, you want to say something?
I'm afraid the only answer I've got is I don't know.
Mm-hmm.
I don't know enough about different theories of gravity to be able to answer.
So we could probably leave it at that. I had a couple of questions for you, Robert. So we know that the ratios of the electric charges are the same across the 3 generations. It is the mass ratios which change in a strange way from generation to generation. So it's obvious. Is that obvious in your picture that the charge ratios will not change, but the mass ratios will change? Can you see that in a simple way?
It's really the difference between, again, I haven't got haven't got enough in these slides here to show it, but it's in the paper. So let's go some of the bits I didn't have a chance to go through. If I can find it. Oh, it's right at the end. I've obviously prepared far too much. This picture.
Mm-hmm.
This is another version of the electroweak mixing angle. So what I've drawn here are the left-handed neutrino, electron, down quark, and up quark, and I've drawn them at an angle so that the charge axis is horizontal. Okay, and I've drawn the weak hypercharge down this way and the weak third component of weak isospin this way. And I've scaled it so that this is a square.
Mm-hmm.
And there is also so perpendicular to the electric charge, there is a neutral charge. Now you can put the origin wherever you like. I think I would probably like to put the origin in the electron, because the electron has electric charge, but maybe no neutral charge. And then the neutrino has neutral charge 2/3. The up quark has neutral charge minus 1/3, and the down quark has neutral charge minus 1.
Mm-hmm.
And then there's a rotation symmetry of this picture that takes the weak hypercharge to the weak isospin, the third component of weak isospin, mixes the leptons and the quarks. Now, I'm not saying that's a physical symmetry, but it's a symmetry that tells us something interesting, because it gives us this angle. So I've drawn phi up here as an angle between, which should really be down here. There's an angle between charge and weak hypercharge. So it should be the Weinberg angle again.
Mm-hmm.
And here's the calculation that says it is.
Mm-hmm.
Well, it's actually twice the Weinberg angle.
Mm-hmm.
Tan of the angle is 3/2, so sine squared of half the angle is a half minus 1/√13, which is about 0.22265 against the experimental value of 0.2229 plus or minus 3. So
this is very interesting. Yes, I agree. Mm-hmm. Very nice.
So
and
I think
no
there's a reason for
sterile
that.
neutrinos, is it? No sterile neutrinos?
No sterile neutrinos, no.
Mm-hmm. So when you say neutrinos are necessary for quantum gravity, you mean the standard model neutrinos?
I mean the standard model neutrinos.
The ones we know of, yes. Not the sterile neutrinos.
I mean 3 generations of neutrinos and antineutrinos. That's it. Yeah.
Thank you. Yeah. I had a more general, maybe a little vague question. I was trying to understand your big picture towards unification. Today you have presented this work, and then you have work with Tavian and Corinne, and before that your own work. So basically I'm asking about your work on E8 and getting E6 from it. Are these something completely unrelated, what you're telling now and what you're doing there? What's your big picture? Why are you doing that as well as this? I'm trying to understand.
I think there are some connections. I've been trying to work out some details of the connections. It's very complicated, and I haven't sorted everything out. Basically, I want a model that is as simple as possible. And I think that what I presented today is exactly as simple as possible and no simpler. I think the E8 models are much more complicated than necessary.
Okay, I get. Okay, I get your picture. I get your picture.
And Octonians, similarly, Octonians don't come into this model here. Everything is associative. I don't need Octonians.
Great. Okay. Yeah. Was there something else in the chat? I think David had written something, and I would read it out. Does the Higgs boson fit into your model? It's a question for you, Robert. Does the Higgs boson fit into your model?
Well, yes. Let's see. It depends how you interpret these things. So you need to interpret the 12 bosons at the middle level so that they have mass. And they still split up as 1 plus 3 plus 9. No, the middle level. The middle level is 1 plus 3 plus 9.
Well, that's 13. No, you want 12.
1 plus 2 plus 9. How does it work? I haven't got an exact allocation of the bosons to the model yet, but there are 12 of them. And at the internal level, you get 8 gluons, 3 massless weak bosons, so the primordial ones are the internal symmetry ones, and there's one left over, which I believe at the internal level is a Higgs boson, because it spins 0. It's a scalar. It's not acted on by any space-time symmetries. So I think, yes, the Higgs boson corresponds to the trivial representation at one level, or to the identity element of the group, or something. Because you can also split up the bosons as elements of the group. So you can take the. So if you just look at the bosonic part of the group, it's the tetrahedral group A4. It's got one identity element, which may be a Higgs boson, or it's got 3 rotations of order 2, which I take to correspond to the weak force, and the 8 rotations of order 3, which I take to correspond to the gluons.
And where's the photon? Where's the photon? In these 12?
Oh, well, maybe in that, yeah, I don't know. Maybe the identity element is the photon.
Okay. So Hilary has some references for you, Robert, on the neutron lifetime anomaly. Hilary, maybe you could please email it to Robert, because he may not be able to record this. And then there's a remark from Daniel that the binary icosahedral group is deeply related with E8 and integral octonions. So it makes sense to investigate quaternionic realizations of binary polyhedral groups and then see the embedding in different integral sets of octonions.
Yes, all of that is true, and I've done extensive investigations of all of this kind of stuff from a mathematical point of view, and it's all very, very interesting mathematically, and I've basically just thrown it all away from the physics point of view. To me, Occam's razor says none of it has anything to do with physics.
Yeah, probably that's why I'm a mathematician and not a physicist. Yeah. So, yeah, but it's very an amazing part of mathematics. Yes, I agree. Yeah.
Okay. There's a question from Tony Bell. Any hints about the exclusion principle in this?
Well, I suppose so. And what happens at the end of the day is the representations, that is the spinors, spinor representations, are giving us quantum numbers, spin quantum numbers, isospin quantum numbers, things like that. They're not giving us particles. The particles should belong in the group, not in the representations. And the group is discrete. That's the exclusion principle.
Johnny, any further remarks on that?
I meant really in the difference between bosons and fermions, that they have different. I can't remember. There's a commutation and commutation and anti-commutation relationships, and one of them is satisfied by the fermions and the other by the bosons.
Different statistics, yes. Yeah. So I think,
yes, it's again a question of how they appear at the three different levels of interpretation. So at the middle level of interpretation, what you've got is oh gosh. No, I probably need to think about this more to actually be able to answer it properly. I haven't done enough work on actually defining all the particles yet.
Okay.
Are there more questions, please? Michael, you there? Michael?
He's fallen asleep.
Or maybe he's remains very busy. Maybe he's attending another talk. Okay, I don't see him. All right. So could you, Robert, if you don't mind, once again summarize your predictions? They were there in the last slide. I don't remember all of them. If you could please see that slide once again.
Predictions. Well, actually, there was. Where did I do the?
I would also like to see that the slide which says, "I have a dream."
I have a dream. Yes, here we go.
I'm curious, what do you have there?
I have a dream that unification of particle physics with gravity is possible. And here are the compromises that I think are necessary. You have to give up general covariance and restrict spatial covariance. And on the particle physics side, you have to give up the Yang-Mills compact SU3 and settle for SL3R. Then you've got SL3R both in relativity and in particle physics, and you can agree and have a unified model. That's my dream.
Very interesting, very interesting.
But you wanted to see some predictions.
The last slide of your seminar.
Oh, the last slide of what I actually said.
Yeah, I just wanted to see what you had. I mean, you showed us, but I want to recall it. The 92 or something, I think. Yes.
It predicts parity violation. It predicts CP violation quantitatively, at least in one instance. I did also, in the bit that I didn't have time to get to, is well, let's maybe just summarize where the parameters come from. I've derived 4 of the mixing angles from particle masses, and there are 10 altogether in the model, 5 of which are in the standard model, and I think there's one new one to mix in gravity. And so where do the parameters come, where the masses come from? I think they have to come from a quantum theory of gravity. Because you can't avoid quantum gravity. It affects every experiment. It's impossible to shield your experiment from quantum gravity. So that's just saying that. And here is the slide that I think says how we can tell that quantum gravity does affect the masses. No, it's not. That's just a preamble. The slide that says what happens, it says the gravitational and inertial mass are different because I've got a mass plane, not a mass scalar. I have in principle 2 independent parameters, gravitational mass and inertial mass, at the classical level. And they were chosen to be equal in 1973. I've read the literature in enormous detail to find out that the gravitational mass and inertial mass were defined to be equal in 1973. And the electron-proton mass ratio is this value, 1836.15 something or other. From 1973 onwards, gravity never again entered into the standard model. That was the last time in which gravity entered into the standard model of particle physics. But the gravitational environment has changed in the last 50 years, and so we should not get this value, 1836.15 anymore. If we did the calculations all over, or the experiments all over again, did everything from scratch, the whole of physics from scratch, I maintain that we would have a value of 1836.45. Which means the gravitational mass of the electrons decreased by 0.016% over 50 years. A heavy metal, which you have to use to measure active gravitational mass directly, has about 0.022% of its mass in the electrons, and therefore you would lose 35 micrograms per kilogram. That is the level of instability in the masses of international prototype kilograms that is observed. So you cannot test this directly because there's some unexplained systematic errors in the mass measurements of standard kilograms of platinum iridium.
Okay.
So I'm predicting that there's a systematic effect on these measurements of mass of lumps of platinum iridium that is of the same level as these unexplained variations. It doesn't predict what is actually measured, but it's a systematic effect of the same magnitude that should be taken into account, in my opinion.
Okay, thank you. Thank you. Bernd?
I have a question concerning the gravitational mass. Could it vary also over cosmic time? Could one look at, let's say, old quasars or old galaxies and compare them with today's galaxies and see whether there's a difference?
I don't think there's any, I can't think of any test that you could actually do there.
Okay.
Because what you measure are wavelengths of photons, which is measuring the inertial mass.
Yeah, okay.
And
That's
I don't
true.
think you can measure the gravitational mass.
And if you look at the rotation curves of old and younger galaxies, this should have a connection with the gravitational mass.
Absolutely.
So maybe you should see a drift in rotation curves according to time. Or to the general environment. Let's say you have a galaxy deep within a cluster and another galaxy far out between, close to a void. Then the gravitational environment will be different. Could this be a test?
I think it could. So I've mentioned that in general terms, this model is similar to a Mond type model of gravity.
Yes, but
specifically to a tensor vector scalar model of gravity. And so, yes, anything that you can use to test Mond, you should be able to use to test this model of gravity as well.
It is totally equivalent. I think the gravitational, I don't know much about Mond, but is the gravitational mass in Mond time dependent, or maybe somebody with more experience in Mond can help me now also for this discussion.
I mean, I think Mond doesn't rule that out, but
Okay.
it's not part of the current formulation of the theory.
Okay.
I mean, the critical acceleration in Mond could, in principle, be time dependent if it is related to the cosmic acceleration.
Okay.
And the cosmic acceleration is, let's say, evolving with epoch. And the Mond critical acceleration is also perhaps evolving with epoch. And that affects the law of gravitation.
But in principle, although I've said this value has changed over 50 years, it's not time dependence. It's dependent on the it's dependent on the solar tides. It's dependent on the fact that the angle of tilt of the Earth's axis has changed by a fraction of a degree over 50 years.
Yeah, but this
and that changes the effect of the tides on the elementary particles.
But in principle, you can get a time dependence after all. The tide of the Earth is related to the interactions between the moon and the sun, and they will accumulate over time. And the same will also happen with other gravitational systems. If they interact over time, there will be different tidal interactions and changes in the gravitational environment, so to speak. So you're right, it's not a cosmic time dependent. It's not because the universe ages that you have these differences. It does not depend on, let's say, not necessarily on the Hubble parameter, but over time, every gravitational system will change its configuration, and also the tidal interactions between the systems will change over time. This is what I mean with time dependence.
Yes, exactly. That's right. So it's a local time dependence.
Yes, confined to the gravitational system as such. It's
Yep.
not okay. I have in a Friedman Robertson Walker model, you can have a cosmic time because it's so homogeneous and isotropic. And I don't mean that it is, depends on the cosmic time parameter, but on the local configuration, so to speak, which might change over time. That's what I wanted to say. Yes. So
yes, exactly.
so it's not a uniform change. I don't expect that this will happen in every so that in every galaxy and in every planet in the whole universe you will see a decrease. You say in the last 10 years. It depends on the local environment, but also the local environment will have some time dependence. That's what I wanted to say.
Yep. Yeah.
Okay.
Absolutely. Yes.
Okay. And this could be something where we can look at also if you look back in time to if you look at old galaxies, because galaxies develop and they also develop their gravitational potential over time until maybe not the elliptical galaxies. They seem to be very much in equilibrium and have reached the final stable gravitational configurations, but irregular galaxies and also spiral galaxies, and especially interacting galaxies. This would be very interesting. So merging galaxies, they really change the configurations of the masses and the gravitational potential. So there should be something in merging galaxies, I would guess.
I would imagine so. I mean, I've tried to interest the Mons community in these ideas and get them to think about how they would test them, but
it looks interesting. So if I would be in Mondian working on this,
anyway, it's interesting that next week and the week after that we'll have two Mon-related talks. Not next week, sorry, the next talk, 24th November, Friday, 2 weeks from now. That talk will be at 2 p.m. London time. Please take note. Not at 4, because the speaker is in South Korea, and he obviously it will be very late for him. So Kyung-Hoon Choi will tell us about his recent work on a test of the Newtonian law of gravitation in wide binary stellar systems. And the week after that, on 1st December, we'll have another talk by Indranil Banik on the same data, testing Newton's law of gravitation in wide binary data from Gaia satellite, but coming to opposite conclusions of Che. So we will, I think, are going to have a very interesting debate because these two authors are making opposite claims and conclusions from the same data. So, so if there are no more questions, I don't know, Michael, if you're there, we could start winding up.
What a talk.
And thank you, Robert, for your nice talk. And then we will meet 2 weeks from now on 24th November.